Hey, so during our high school, we do all sorts of calculus, whatsoever, but there are some geometric aspect we always miss. And this confusion usually occurs when when we deal with specific shapes and if we want to figure out their height or other stuffs. That's when those things actually happen. So you can see this cylinder right here. You can see a trapezoid shape, right? And you can see a trapezoid shape. A trapezoid shape here. So before starting what I want to do, we all know about arc length, right? We all know about this. ds equals to dx square plus dy square. We all know that, right? And then if we want to take common, some sort of, then we take this. And the dx stays here. Right? We all do that. So now there's an interesting aspect about it. We use this term as arc length in a curve, right? We use this as arc length in a curve. We have two curves there. So this is you can think of it as a cylinder with a trapezoid shape here. Like you can see that in here. Probably. Like if I just dash here, do some dash line here. You can see a trapezoid here. So what we want to do, like in calculus we deal with infinite small length of an area, small part of an area. We call it infinitesimal, like like here, like this. Like in a curve, you know, what we do is like, you want to do it, we divide it into small arcs, like this. We do that, like these are small arcs. This rectangle has a small arc area of dA. So for the same case, we will also do that here. Like for example, I want to figure out this shape's area. Now here we have a thin trapezoid, and now you can call me, how can it be a trapezoid? The trapezoid has things like this, right? But you need to understand, the surface has two circles, a curved line. We have two curved parallel lines. See, these things we'll understand if we study spherical trigonometry. Like that, it has lots of those topics understanding. Hopefully I'll make a video about those things, but let's keep it about here. So we want to find the small strip area from here. We call it dA. You see, we can call this thing as a trapezoid. How? These two curved lines are parallel. We have two parallel sides, so we can call that a trapezoid. Yes, we can call it a trapezoid. Now you can argue with me like this. Why aren't these slant lines are parallel? Well, these are not. You can see that from here. Like these lines change from here. This. These lines change. So these slant lines are not parallel. Okay, if we want to figure out the area of this small thin trapezoid, okay, we figured out the parallel sides, But now what? We need to figure out the height, right? Now, what is the height? Suppose this object is in 3 dimension. So I'm choosing this Z here. This is Z axis. So now what I will say is we will take the slant lines as the height. Now you can ask me why? Why do we take the slant lines at height? Look at it. These slant lines give the distance between the two surfaces. And what does the height give? Height gives us the minimum distance from these two sides. And these slant lines will give us the minimum distance from these two surfaces, right? We'll use the slant line from here. And we will call this slant line as ds, right? It is ds. This is the length. This is the length of an arc. This is the length of an arc. Okay. And also, this circle has radius, suppose x, right? But when it grows from here, the radius will not be the same, right? No, the radius will not be the same. It will not be the same. Now, if we want to think of something here, like you can see this circle is bigger than this, so the radius should decrease. I'll tell you to assume that this has the bigger radius. Big circle. And this is the small circle. Just assume, don't take it seriously. Okay? So here the radius increases, right? Circle from small circle to big circle, the radius increases. And do you see the relation? The radius is proportional to the distance from the Z, right? As the Z increases, the radius will increases. The radius x is a function of Z. We can say that, right? Yes, we can say that. Okay, now here comes the more important part. The important part here is, you see, this, if we connect these two points to center, this create an angle phi, right? So for a small strip, we'll take that d phi, right? For a small strip, we'll take that as d phi. So in here, the radius is x of z, and the uppercase, as we're taking a small size, a strip size, so here the radius is x of z plus dz. That's what the radius is here right now. Okay, now our job is mostly done, not mostly, almost done. So in the parallel sides, what is the length of these parallel sides? Right? What is the length of these parallel sides? It's an interesting question, right? So here, we all know in the circle term, if this is phi, and this is x, z, then the curvature length is x of z into phi. So for the upper surface, the curvature length is x of z. No, sorry. Rubber is very smooth in one note. That's very impressive. So in the upper surface, it will be x of z plus dz. Oh, I forgot to mention, it should be d phi. Okay, d phi, because we are taking small strip, that's why. Okay, so now let's move to the area part. We know that half of the parallel sides and into the height. Sum of the parallel sides and height. So what do we have here? We have x of z, the phi. So we also have x of z plus dz, the phi. Okay. So at the height is the slant length. So our height is ds. So what is ds, by the way? So we know that we have dx square plus dz square. Okay, because the curve is based upon that, so we can take it as plus dx dz. You can see it from here actually. Plus dx plus dz square dz. Oops. Small dz. Yeah, I guess it's fine now. Yeah. So that's our area. Now we can approximate that. We can approximate here, I guess, that x sub z plus dz we can approximate as x of z. Why? Because this increment is too small, right? So if we take the average of these, then what we will get is x of z d phi and into 1 plus dx dz. Okay, and yeah, so that's our answer. Or in that case, we can do the thing here, like if you want to take the dx out of here, you can also do the same thing. So yeah, that's our answer. That's how we do it actually. So what we do is the x of z, we simplify it, dx dz square into d phi dz. That's the area of the thin trapezoid we have here. It's a very interesting game. So what we can learn from this video is that, like in this case, in this video, for the height of the trapezoid, you might have asked me, why didn't you take z here? Because we are dealing with a curved surface here, not a plane. If we deal with the plane surface like this, suppose the surface was like this, and we had something like this, then I would have taken dz. But this is a curved surface now, and we have a angle phi here. See these things we use in the spherical trigonometry in coordinates. We use this angle as azimuth. It's a very important angle. Like this shape is inscribed by it. So yeah, that's it for today. So our lesson from is today that the height should not be always a straight line. Like what do we think of height? It should be a straight line from the one point to another, but that's not the thing. Height can be like this, but it should have other parameters to define that, and we got that. Okay, here the slant line was our height between the surfaces. And yeah, so we got the area of the trapezoid. So this is the geometry we all miss. Okay, this type of geometry we all miss in calculus. Like, this is very important, and these things, aspects, and these perspective of, like, you just take this angle by yourself, like, and this approximation also at a small strip length here. So yeah, that's it for today. Hopefully you liked it, and we'll come again with a new video. Today's topic was a bit messy, but it's very important.